All right. Okay, now we should be going. If somebody can just type in the chat box if they can hear us okay. We are fortunate that the internet came back at Iowa State University, so we're able to do this and I think have the virtual option available and not be running off of somebody's phone. So welcome to the March session of our Iowa Nutrient Research Center seminar series. And this month we're going to hear about bioreactors and then oxbows and ditches. And so it's my great pleasure to introduce a colleague of mine from the Department of Ag and Biosystems Engineering, Dr. Michelle Soupir, professor here, and also the Interim Associate Dean of the Graduate College. And Dr. Soupir has been active in bioreactor research for about the last decade at least. So I'll turn it over to Michelle.
All right, thanks. And hi, everyone. Thanks for coming out. And I'm pleased to kind of give an overview of our INRC funded bioreactor research. As Matt said, we've been working on a variety of projects over the past decade. And today I'm going to focus on our pilot scale bioreactor system. So it's kind of fun. I went back through the proposals to see what we called these at different times. And the very first one was called experimental bioreactor installation and research. And so this first project was really directly funded as an outcome of the Iowa nutrient reduction strategy. And for those who may not be familiar, a bioreactor is essentially a pit that's filled with a carbon source, typically wood chips, and tile drainage is routed through this wood chip bioreactor. And this is an ideal condition for denitrification to take place. So there's a carbon source which keeps the microorganisms happy, anaerobic conditions, so they use the nitrate as their oxygen source. And in these systems, we see removal of a lot of nitrate. They're really nice for implementation into agricultural landscapes because they can be positioned at the edge of the field, so they don't take a lot of land out of production and they don't require a lot of change in management practices. I do want to acknowledge that Natasha Hoover did help me create the slide set. So a bioreactor installation in Iowa was already underway when I joined Iowa State as an assistant professor in 2008. So the first bioreactor installed was in Greene County. And initially adoption was at a pretty slow pace. So the INRS annual progress report would show that there would be about 3 bioreactors and saturated buffers installed per year for quite a while. And we used to say that if a bioreactor was installed, it was usually worthy of a news article. So there were a lot of, local news articles when a bioreactor would be installed. And so that was great. But we also know that to meet the goals of the nutrient reduction strategy, we needed a lot of bioreactors. Some estimates are over 100,000. And so hopefully with this research, we can help inform and contribute to the kind of building of momentum that we're already seeing. So by 2018, 19 practices had been installed. And then a really innovative team kind of came together in around 2000 with this batch and build concept, which is taking down the barriers and helping to get installations of practices really rolling and moving forward at a much faster progress, targeting 50 practice per year in some areas. And then these strategies are really expanding throughout the state of Iowa. So you can see we've seen a lot of really great progress. So let me kind of step back and talk to you a little bit about how we went about designing this kind of unique pilot scale system. And again, Natasha Hoover was hired as staff in my research group at that time, and she really did the design and oversaw the installation of this entire system. In talking with John Lawrence at the time, he said, we really want a system that's unlike anything else in the world. So we had a pretty good direction that they wanted a really unique system where we could study pilot bioreactors in parallel and really learn how we can manage these systems to enhance denitrification. So to give you an overview of how this worked, so the water source is a drainage district line that runs through that Ag Engineering and Agronomy Research Farm, which is located just west of campus. And from that, we pumped water up to some large tanks. If you drive by the site, if you drive by Biocentury Research Farm on Highway 30, you'll see some black tanks off to the south. That's our pilot scale site. So the water is pumped up to those tanks. At the inlet of the bioreactors, we have flow control and we have a dosing port so that we could add other chemicals if we wanted to. The water then flows by gravity into some watertight concrete trenches, and then we can collect samples throughout the reactor and at the outlet, where they then flow into some agri-drain control structures. So I have some pictures of the installation to just kind of walk you through the progress. So again, lots of people were involved with the installation of these bioreactors. The concrete troughs came precast and were installed by Construct. That was the contractor who did the work for us. You can see that they were essentially dropped into the excavated area, sealed up. Then in the middle, these are the stilling wells, or the sumps where the water flows out of the bioreactors. Here, the wells are installed so that you can see where water quality samples could be collected along the length of the bioreactor. Here we have the drain structures, and those are used to control the water level in the bioreactors. And then the College of Engineering did a photo shoot out there in about 2016, and those have been just nice pictures that we've used a lot of times. So you can see here, we have bags of wood chips that we've stored in these wells so that we can get samples of the wood chips more easily. And then here, Emily Martin's collecting a water sample. One of our students Emily Martin had a drone, so this is kind of the aerial view. So again, the water is pumped to the black tanks. It flows by gravity to the inlet of the bioreactors. You can kind of see the scar on the landscape where each of the 9 bioreactors are located. Points A and B are those stilling wells. And then we then began collaborating with Tom Eisenhardt and Morgan Davis. So we installed rings for monitoring greenhouse gas fluxes. These are the outlets where we collected the outlet sample, the stilling wells, and then these are those large sumps where the water is then discharged downstream into the same tile drain line. So 2017 by this time, and we're out of money and it's time to start doing some real research. So wood chip bioreactors for improved water quality, and again added Tom Eisenhardt and Tom Mormon to the team. And we had 2 students that worked on the project, Emily Martin and Morgan Davis. At this point, we had to make some decisions about what's this experimental design going to be for the next till current date is really what it is. And so we used a randomized block design where we have 3 different blocks, and then within each of those blocks, we use 3 different flow rates. Hydraulic residence time of 16 hours, 8 hours, and 2 hours. And so we wanted to see this kind of represents a range of pretty common residence times that we see in bioreactors. And then we measured the nitrate removal and then the gas emissions. So we measured the gas flux through those rings, those surface rings, and then we also measured the dissolved gases at the different points within the bioreactor. Okay. So this is a figure that Emily Martin put together, and I think it does a really nice job of kind of helping pull together some conflicting information that we have when we think about bioreactor performance. So we can think about bioreactor performance as a function of the mass removal rate, which I just have as removed here. Or you can also see a percent removal or a percent mass removal rate. And And those give us very different bits of information. And what we have to consider with this is also how much water is going into the bioreactor. And so we really had an ideal way to measure this. So the total flow to the bioreactor was about 46,000 liters per day. And so that was the capacity of a bioreactor that was flowing, at a faster flow rate. So it only had a residence time of about 2 hours. The 8-hour residence time could treat, about a fourth of that amount of water. And then the 16-hour residence time would treat about half of that amount of water. Okay, so there's a lot less water that can actually ever get into the bioreactor when that residence time is much higher. So we look at this data in 2 different ways. So when we look at the total mass removed, we could see that more mass nitrate is removed on a daily basis when we have that higher flow rate, or that 2-hour residence time, about 9.3 grams per meter cubed per day. When we looked at the 8 and the 16-hour, we saw a decreasing amount of mass removed. Some studies have, kind of called this as a wash. In this case, we're very closely able to control and measure the flow, control conditions, and these 3 conditions were statistically significant. So at the higher flow rate, we have that higher mass removal. But it's important to also think about what is the percent removal when you only consider the inlet versus the outlet, because this is often reported in the literature as well. And so when we look at that percent removal, 9% for 2 hours versus 54% for 16 hours. So again, if we don't know what that mass, what the total flow conditions are, a bioreactor with a much higher residence time is of course going to show a much higher nitrate removal percentage. And so but it has such a smaller potential as far as the amount of water that can actually be treated, that the overall mass removal is actually less. So, and that's demonstrated by, this is the bypass flow, so the amount of water that goes around the system relative to the amount of water that actually can enter the system. So based on this, we would say, well, shorter residence time, let's get as much nitrate out of the water as we can. But we had partnered with Dr. Eisenhart and Morgan Davis, and we looked at that greenhouse gas measurement. So when we looked at the surface flux, that data was not really, just didn't show anything real different compared to kind of standard agricultural practices. We didn't see a lot of surface flux of nitrous oxide or methane through the bioreactors, which has been shown by others. But then we also measured the dissolved nitrate oxide and methane coming out of the bioreactor. And this was where it got interesting. So because of that higher flow rate, we're going to see less or more incomplete denitrification. So that meant that there were more intermediate chemicals such as nitrous oxide coming out of the bioreactor. And so unfortunately, nitrous oxide has a really high global warming potential relative to carbon dioxide and methane. And so because of that, the global warming potential of that 2-hour residence time bioreactor is much higher than the 8-hour and the 16-hour. In fact, 8 and 16-hour weren't different statistically. So what does this tell us? This says that, first of all, it's kind of potential. So is that dissolved gas, does it off gas right away when it discharges into a stream? Does the denitrification process continue? We didn't measure that, especially in a tile drain line, but there's certainly more potential for off gassing or of emissions when we have those higher flow conditions. So based on that, we kind of landed on this 8-hour residence time. With removing nitrate, the last thing we want to do is convert a water quality concern into an air quality concern. Okay, so now it's it's 2018 and we need a new sexy idea to keep the INRC interested in our pilot scale reactors. And so we had been interacting and talking with Gary Fireisen, who's with USDA ARS in Minnesota. And he had done some really interesting lab experiments showing a great potential for corn cobs to remove nitrate in these types of systems. And so in working with him, we came up with this experimental design to dig out part of our bioreactors, not the whole thing, and just replace the front either 25 to 75% of the wood chips with corn cobs. And so you can see within that blocking structure, we took to 25% of these three and then 75% of these three. It was a really cold, miserable, wet day. Everyone, it was like, you don't get a choice. You have to come to the field today. So, and again, this is another example of so many people that had to help out. As we did this, as we were out there digging out these wood chips, we took advantage of the opportunity to look at the wood properties and see what's going on with those wood chips with the bioreactor depth as well as the length. So we took samples at the inlet across these 6, at the 25% across these 6, and then at the 75% across these 3. So here's some more pictures, but essentially we use these post-hole diggers to get samples from 4 different depths. And then we tested these wood properties for a range of different things, and we did some microbial community analysis and looked at some common denitrifying genes. And so what we saw is, and this was Abby Schaefer. So here's a picture of Abby, and she published 2 papers, one on the carbon properties and one on the microbiome. But red means essentially degraded wood quality, yellow and orange is less degraded. So we saw at the inlet of the bioreactor, those indicators started to show that those wood chips were breaking down much more than the wood chips that were located at that monitoring point B. And so, maybe we just need to excavate instead of digging the whole thing up. Maybe we can just replace that material near the inlet of the bioreactor and reduce that recharge cost. And so here's what the fresh corn cobs looked like. Again, we had another contractor come help us with this piece of it. And this kind of just shows the open bioreactors. And then, so this project, we've had 4 years of data on the performance of the corn cobs that were integrated into the bioreactors. And it's been kind of a crazy, we had COVID, we had a drought. So 1 year, and actually there was a funding gap the year that it was a drought. So we had no samples anyway. It was amazing that it lined up that way. But then we were renewed last year and we got some more samples. And so this is a lot of data that's kind of contains, different years all combined. But what it is showing is that even after 4 years, when we look at kind of that median nitrate removal, the corn cobs are still performing very well. And so we're planning to continue to monitor this summer. And you can see kind of these removal, so that percent removal ranges are over here. So this is 0, 25, 75% corn cobs. And then these are the 2, 8, and 16 hour residence times. Okay, so key findings. The higher flow, more nitrate is removed. Also, more greenhouse gas production potential through the dissolved state, not necessarily a surface flux. We saw more quickly degraded wood chips with that higher flow. And I didn't show the figure, but there are microbiome differences between bioreactors with different flows. And we see that corn cobs are still working well 4 years in. So what's next? Just we've been able to really build upon this work that's been funded by INRC in many different ways. One is a new INRC project funded with Dr. Adina Howe as the PI, so expanding on that microbiome and looking at some different carbon sources to try and see what role that microbial community is playing in the denitrification. We've partnered with Billy Beck. This is maybe my favorite photo shoot of all time that Sarah Hayes did, Billy in the woods, but kind of managing those forest resources to pull out lower quality woods and then have those on site for bioreactors. So there's a lot of outreach and extension with those grants that are funded through US Forest Service and NRCS. And then we also have a project on a pumped bioreactor system, which Lindsay Hartfield has done a few webinars for Dr. Helmers on that topic. So just there's a lot of fun and exciting ideas, and it's fun to see how much bioreactors are really taking off and continuing to be installed across the state. We've had really great impact on students. So a lot of different students have worked on these projects and published, of course, their research for dissemination, but are pursuing careers related to conservation practices and bioreactors. And so then this is a list of the publications, and I think I stayed on time pretty good. So
okay, are there
turn this over to
questions for Michelle? I think we have time for a couple questions right now. So if are there any questions in the room to start with? Give that. So, okay, I'll take my prerogative as moderator. So the corn cobs have probably not been in long enough to start to see whether we start to see any decline in their removal efficiency or their performance. Am I correct in
well, that? We're not, they're definitely still outperforming the wood chips, and we are not necessarily seeing a decline in their performance yet. Okay. So 4 years, this will be year 5. Okay. And Jiao Law is here. He did do an economic assessment of the corn cobs, and that was one of the things that we were estimating, how long they can survive with, we didn't really expect past 5 years. Yeah. And so I'd say they're doing well.
Do you see any signs up? Have you seen in either of the cases with the wood chips or now with the corn cobs any subsidence in that first?
Yeah. So when we dug those sections out, we did measure the subsidence, and we did see pretty significant breakdown, especially at the inlet of those wood chip bioreactors. And then Jiao, are the corn cobs also subsiding?
Yeah, for everything. So including the compost and the chips, and that had to happen during the first few years when soil have to be arranged.
Yeah.
Whatever that comment was, could you repeat it for those of us on Zoom?
Yep. Yeah. Which I think Michelle can summarize that for you.
So we are seeing that both the wood chips did subside early on. So soon after installation, within the first few years, that's when we do see the majority of that subsidence. And then the corn cobs are also beginning to subside. And again, within the first year or two is when we saw the majority of that. So.
All right, I think we'll move on to Dr. Schilling. Let's thank Michelle. And then we need to ask Michelle a question if you have one burning at the end.
Okay. What was the wood?
So
what type of wood?
It was a mixed.
It was a mix. So our next presenter is Dr. Keith Schilling. And before I turn it over to Keith, Kay is going to pass out. If you can put your name, for those of you in here that aren't a speaker, put your name on the sheet, and you'll be in the raffle for an INRC coffee mug. If those read my email from earlier this week, that's why maybe we had a couple more people show up. So we're really fortunate to have the state geologist for the state of Iowa with us today, Dr. Keith Schilling, that is with the Iowa Geological Survey. As I said, the state geologist at the University of Iowa with IHR Hydroscience and Engineering, I believe, as well, affiliated there. And Keith is going to talk to us today about roadside ditches and oxbows as nutrient reduction opportunities.
Thank you, Matt. Pleasure to be here, the crowd here, and whoever is online. With the time that we have, I tend to like overload stuff, so I'm going to go pretty quickly just to get through as much as I can. Why are we here? Of course, we've got a nutrient issue related to our export. This is a classic figure that my colleague Chris Jones prepared a while back, just showing Iowa's contribution to the Gulf of Mexico and the contribution to the Mississippi and Missouri River basins. It's quite sizable. So we need to look for opportunities in the landscape for nutrient reduction. Michelle talked about a managed system of bioreactors. As a geologist and a landscape person, I take a different perspective and essentially look for opportunities on the landscape for water quality treatment. So in this diagram of a standard air photo, probably from eastern Iowa somewhere, we have a lot of these systems where water and nutrients leave the edge of a field and they're following the water downstream, downhill to the river system. So they collect in waterways. We have roadside ditches as conveyance systems. These coalesce on floodplains, and we have oxbows on floodplains and so forth. So in future efforts, we are doing a lot of work on waterways. So this is a topic of a future presentation, and we've done a lot of things on floodplains, but this presentation today is going to be focused on 2 locations downstream of the edge of a field where we see opportunities for nutrient reduction benefits: roadside ditches and oxbows. Why roadside ditches? Everybody here has traveled our roads, fine roads of the state. Every road is lined with ditches on both sides. So they are effective conduits for non-point source pollution delivery across the landscape. They cross topographic boundaries, they concentrate flow. Do they provide any nutrient reduction benefits? Do they provide water quality benefits? Are they considered biogeochemical hotspots like you might see in wetlands or riparian buffers? So that was the question we posed. As you drive around, you constantly see these things and they're conveying water and nutrients. What function do they have? So we approached the Iowa Nutrient Research Center, and I should have had the date, 4B. Yeah, something like that, 15 or 16 or so forth. And said, okay, what are these opportunities for nutrient reduction benefits? We're not talking about streams and watersheds that drain streams that cross roadsides at bridges. We're talking about catchment areas that drain into a roadside ditch, and the roadside ditch is the conveyance of that watershed area to the stream. Are there opportunities in that spot? You might wonder first, like, how many areas are there like that? Well, we did a study that focused our effort in Lime Creek watershed in eastern Iowa. So the town of Independence is there as a county seat for reference. It's in the Middle Cedar watershed. And so we looked at 6 different locations where we installed wells, we collected soil samples and monitored over the course of a year in systems that range from a gravel road to a paved road. There were some differences there that I'm not going to talk about. But in this case of Lime Creek, 30% of the watershed first drained into a roadside ditch before it made it to the stream. That's not insignificant. That's a lot of areas. It's not very often we get to treat essentially 30% of a Huck 12 watershed as part of this treatment train. And that's not that's not a number that's unique to Lime Creek. I think there was somebody that did some work in the East Coast and found a similar number, like in New York State, I think. These roadside ditches are repositories for all that sediment eroded from the farm field to be deposited in the ditch. You can see from the soil samples there that we see a fine organic rich deposit from the eroded fields sitting on the native topsoil, in this case, or subsoil. The sedimentation from say 27 to 31 centimeters. So there was a sizable pile of eroded material in these ditches. Again, not unusual. Many of these are even over excavated over time because they collect so much eroded material. So they're loaded full of carbon and nitrogen and so forth from the eroded soils deposited in the ditch. At our 6 different roadside sites in Lime Creek, we installed wells, put transducers, monitored water table fluctuations. So now we have organic rich sediments. Water tables are often very high, less than a meter below ground surface. So they're very well saturated. They tend to dry out in the summer, no big surprise. And in one case, we had a tile that was feeding the ditch, providing a constant source of water until it ran out. Until it went dry, and then the water level dropped and then picked up again when the tile started flowing again. So now where they're organic rich sediments, they tend to be very saturated. We did groundwater monitoring in these ditches, and where we saw nitrate, there was removal as water would flow down this ditch system. 4 of the 6 ditch sites had nitrate reduction. 2 had no detectable nitrate to begin with, but on average, we saw about a 60% reduction in nitrate concentration in the subsurface in these ditches. What's the potential for nitrate reducing capacity? If you consider the ditches with reduction at 60%, we measured infiltration rates at an average of about 0.3 millimeters a minute, looked at some background surface runoff nitrate concentrations and said runoff from the field with a nitrate concentration of this, with this infiltration rate and this sort of reduction, we see a rate of 0.2 to 0.4 grams per square meter per day, which are similar to what you see in many cases oxbows, which we'll talk about, in wetlands and so forth. So there is potential here. Might be something to think about, something to enhance down the road as we consider other opportunities. We published some of this work in the Science of the Total Environment, and have had discussions talking about what can we do to enhance this ditch processing capacity. The Iowa DOT is kind of interested in reducing erosion and other things in these roadside ditches. Are there opportunities for further enhancing nutrient reduction? Well, we approached the DOT with a talk such as this, and they took this opportunity to do what engineers like to do, which is to engineer things. And they said, hey, and I said, one of the things we could do is a 2-stage ditch. They like that idea. So we've parlayed the Nutrient Center funding to talk to the DOT about getting a 2-stage roadside ditch installed as part of the Highway 30 expansion to 4 lanes. There's a stretch of Highway 30 near Prairie Creek that has a small stream draining about a square mile of area, and said, let's convert this small perennial stream into a roadside 2-stage roadside ditch. So there's the view of the pre-construction. We did some preliminary designs. Antonio Arenas is here, and he's helped with some of these calculations, and other folks have as well. So we came up with a plan to convert the standard ditch into a 2-stage ditch. Again, it's a whole subject of another talk that I'm blasting through here, but this is in general what we've done. With Antonio's help, we did some preliminary models just to see for a standard flow of 90 CFS. You can see in the cross section on the left where this same amount of flow would go from the edge of the road back into the field and be outside of the ditch. The same 90 CFS with this 2-stage construction would all be contained within the channel, and we'd have this additional capacity to capture dissolved constituents as well as the particulate phosphorus and so forth. So we've since this preliminary design, construction has occurred. Construction was as part of the roadside or the 4-way or 4-lane expansion of Highway 30. has gone forward. The ditch has been built. We're in the process of post-construction monitoring. For those of you considering monitoring in conjunction with highway construction, let me just say it's not ideal. There's a lot of issues going on. We're working through those, but it has been built. There's the first stage there. We left the channel as is, and then just built this extra bench on either side of the channel. So we've got upstream, downstream turbidity. We have flows. We're doing ISCO grab samples and so forth. So there'll be a lot of monitoring this year and next, provided that we still get access here. Okay, so that was the roadside ditches. I'm going to move forward here. Following the water downstream, we've got the water into the ditch, into the stream. What about Oxbows? This is another INRC effort to fund work into capturing the nutrient reduction benefit of multi-purpose Oxbows. We call them multi-purpose Oxbows. That was not the original name for restored or reconstructed Oxbows, but we call them that because they have a lot of ecosystem benefits. So it's not just a water quality benefit. Fish and Wildlife Service and the Nature Conservancy and Iowa Soybean Association have reconstructed hundreds, maybe 100, 200 Oxbows in north central Iowa, primarily on the Des Moines Lobe for the federally endangered Topeka shiner. So they've been constructed for this important habitat benefit. We joined this effort later to see what sort of water quality benefits, what might we see in these systems. Here's primarily, they've been concentrated in the North Raccoon and the Boone. This work predated INRC funding a little bit. This was work funded by the Nature Conservancy, but we looked at an Oxbow in the Boone River watershed in the White Fox Creek, and we looked at monitoring this restored, reconstructed Oxbow right there, the curve-shaped structure. We installed monitoring wells upstream, up gradient, down gradient. In this case, this Fry Oxbow, named after the landowner, had 2 tiles that dumped into the Oxbow, delivering a constant source of nitrate and water to kind of turn over the water in that system. So we used this combination of mostly grab samples and the monitoring data over a couple-year period. And we found that the nitrate reduction benefits in these Oxbows range from around 40 to 45% over these 2-year period. You see that the reductions occurred primarily, late summer-ish when things warmed up and so forth. The efficiencies increased to darn near 100% in that case. Published the results in Ecological Engineering. We did a follow-up study on the Fry Oxbow. A year later, in this case, we deployed a Nitrotax sensor in the Oxbow. Here in the upper left is the sensor data. You kind of see how we're able to capture now some of the fluctuations in the nitrate concentrations. In this case, we quantified inflows and outflows and said that nitrate reduction, again, like our ditch, was about 0.2 grams per square meter per day, and the efficiency was 35%. So gathering more data, we have one site we've looked at over 3 different years, ranging from 35 to 45% nitrate reduction. Again, we haven't approached the INRC funding, but with some other work with the Fish and Wildlife Service. This is Alicia Kenny right here with the Fish and Wildlife Service doing the grand direction on that. We had a student, Bryce Haynes, at the University of Iowa. We looked at another Oxbow site in east central Iowa by Cedar Rapids in Morgan Creek Park. You kind of see the scar here in this air photo that Bryce took with his drone with Alicia's help and the city of Cedar Rapids, the Lynn County Conservation Board. They installed an Oxbow on Morgan Creek. The unique thing in here was that this was an Oxbow that's fed by overbank flows. There's no tile drainage in here. So it's an interesting contrast between an Oxbow fed by tile drainage, in the case of what we looked installed. Bryce ran up there after an event, installed Nitrotax sensor in this system, and you see over the course of 3 weeks, so if you compare the two systems here, we had a tile fed one on the Fry. Morgan Creek was overbank flooding. You kind of see just from the comparison here of these systems that nitrate concentrations were much higher. Of course, when the tile fed site, excavations were similar. Seepage rates were higher in Morgan Creek and that off the lobe landscape. The important thing is to look at the load. So we had the load, or the mean concentrations of the Oxbow were much higher, 4 to 6 in the Fry, less than half, or half a milligram per liter in the Morgan Creek. The loads were very different. So we saw up to 470 kilograms of nitrate into the tile-fed Oxbow and only 15 kilograms in one flood. And like Michelle noted in terms of the efficiency, well, we got greater efficiency of removal when it didn't see much nitrate. So in this case, we saw greater efficiency in the non-tiled Oxbow. The costs would have been a lot similar. It was higher for the Morgan Creek site because they took the dirt away in trucks and used it for another part of the park. So the trucking costs were much higher. All right, so now with that background, we're going to go into new work funded by the INRC, where in this case, we looked at designated paired, tile-fed, and non-tiled Oxbows. Worked with other ISG folks, Clay Pierce and Tim Stewart, looked at fish and habitat wildlife benefits. And we had 4 systems in north central Iowa. Nutrient concentrations in the tile-fed sites were actually in all the sites. You kind of just see in that box plot here, the tiles, of course, were delivering much higher concentrations. Groundwater was really typically very low input. And the Oxbows, and with and without tile drainage, were very different. We looked at phosphorus concentrations here, but in the end, they were not all that high. So it was hard to track that sort of mass movement through these systems. The monitoring results were very similar to what we saw with the other tile-fed sites. They did see substantially greater nitrate influx, from 50 to over 220 kilograms. We put nitrate sensors in these 2 tile-fed sites. You kind of see the fluctuations that occurred here in both of these McClellan and Sanders sites with tile. The non-tile hardly ever saw much nitrate. So really, it kind of emphasizes this multi-purpose benefits, that for this to be an INRC practice, it needs to see the nitrate. If you look at load reductions, I'm just going ahead here, my time is running out, but we did add these 3 or the 2 tile sites here from the INRC funded work to the 3 other years monitored at the Fry Oxbow. We'd have a combined 7 site years at this point. And the efficiency that had been about 40 to 45% increased now to 62%, plus or minus 19%. So we have an updated numbers that we can use on the practice list. We have published some of this work. We've published several things related to this, but with our collaborative effort, we did publish a new paper that highlights this multi-purpose Oxbows as a nitrate treatment practice. It's now made it to the INRC practice list. The key part here is that people could put in Oxbows for a lot of benefits, habitat for the fish, wildlife benefits, and so forth. But for it to be a nutrient reduction practice, these need to be engineered to see tile drainage. So that's the multi-purpose benefit for the nutrient reduction strategy. So in conclusion, our INRC work at the Iowa Geological Survey has really essentially been off the edge of the field and following the water as it's moving across the landscape. We'll have further work on waterways that we're looking at. We've been involved in floodplains. We're helping Dr. Billy Beck for some of his floodplain work. So we're going to continue to follow the water downstream from the edge of the field, but there are other opportunities for nutrient reduction benefits, including roadside ditches, which I think are underutilized for their effectiveness. Not that we need to go to the two-stage roadside ditch, but there are ways to enhance the nutrient reduction benefits by slowing that water up, increasing infiltration, and making use of some of those deposits there. And the multi-purpose benefits, multi-purpose oxbows are showing great promise for treating tile drainage. And all indications are landowners seem to like these practices because of all these ecosystem benefits that they provide. So future work will focus on the waterways. Stay tuned on how that's going. We'll have more data to share on that later. Acknowledgements, IGS team involved, Matthew Streeter, Sophie Pierce, and Jason Vogelsang. Students have been involved. We've worked with Co-College and Iowa Soybean Association for their lab services, funding from INRC, Nature Conservancy, and so forth. And then we had help from Justin Meisen from the Tallgrass Prairie Center to do the vegetation surveys. So it's been a very big collaborative effort on both these projects. And then with that, I will take questions.
Questions for Keith? The question was,
yeah,
the
go
question, I'll while you put the answer, the question was what the cost difference was for the two-stage ditch versus if they had just done something and normally cleaned out that ditch.
It was included in the design of the Highway 30 expansion, so it was kind of hard to pull that out. I know it was physically constructed in the matter of like practically hours, you know, with their heavy equipment. So that was very little. And most of the cost at this point is going to be our time to get it all monitored. So I think the design wise, it's probably a fair bit of cost up front to figure out the dimensions of that. But the actual construction is really wasn't very much for the heavy equipment that was out there.
Not to interject, but I think that some of that work that you're doing with DOT is an example of how sometimes you give a presentation and you wonder, is it worth it? But you gave a presentation on some of your roadside ditch work to the Water Resources Coordinating Council, of which DOT is one of the members. And I think afterwards, you know, you'd maybe tried to get into DOT, and just that presentation connected them that we need to have more discussion about this. So.
And there is a lot of interest in this ditch work with the roadside management group in the state. So again, don't fixate on the two-stage thing, but just in terms of managing vegetation for nutrient reduction benefits in these ditches, there's a huge interest in that. So counties have approached us, and maybe with this some new funding model that we're going to work with, maybe there's opportunities to expand and work with some of these counties, but there is a lot of interest in managing roadsides for nutrient reduction benefits.
So, Matt,
Bill.
I'm not sure, Keith or Matt. So if I recall, on the two-stage ditches that are frequently implemented in drainage networks, a significant amount of the cost of those ditches is the easements. And that may simply not be the same issue in the roadside ditches. They may have a sufficient easement. So do you think that's the case, Keith?
Yeah, it definitely was in this case with the easements on the Highway 30 expansion. We were well within their right of way. We had scoped out some other sites that were going to be probably pushing the envelope a little bit about, is there enough room in the roadside to do that? But this larger road system, there was plenty of room. So I don't think it's a universal, but I know in the larger roads that you would have plenty of room.
There was one more question here about the sampling interval that you used.
Yeah. Well, we're gonna make it definitely an event-based system on the roadside, just because on that small watershed, it was incredibly flashy. The nice thing is that we'll have turbidity sensors upstream and downstream in that system with every, I don't know, minute, 15 seconds or 5 seconds. I don't know what frequency they set up, but we'll have a super high resolution of continuous turbidity. The grab samples probably we'll need to figure that out.
We got one more question, Ann.
With the roadside ditches, did you say anything about the plantings and how the different plant cover changed nutrient process?
Yeah, we looked at that. That was what Justin Meissen did. So we have really good veg surveys for those 6 sites, but we only had 6 sites in one watershed. So there probably wasn't enough to really tease that out. In cases where it was heavily wet more often, we had a cattail issue on some of these. So it's like, we're still working that out. And that's where I think the future direction needs to go is the vegetation approach, management for greater benefit. And that's where there's a lot of interest from the roadside community to do that.
All right, we have reached 4 o'clock, so I want to let's thank Keith for his talk. For those online, your time is done, but for those in the room, we got the raffle for coffee mugs. We'll look at them. 1, 2. We have Xiao and Chris Raymond. Oh, Chris,
I have one.
you have one. Yeah, okay, that's right. You have one from last time as a speaker. Antonio. Yes, all right. All right. Thanks everybody for attending. Thanks for those online.
All right.
You want to add your collection?
Yeah. So it seems like there, you said at one point, the flow, like what Michelle's talking, if you slow it down,
Thanks,
it'll get
Michelle.
better
Yeah.
benefits. But isn't that in direct opposition to what DOT wants? We want water gone.
Yeah.
So yeah, it's a trade-off there.
Yeah, definitely. Well, I think